Thank you. Welcome, everyone. First, I would like to thank Cooperative to invite me to have this seminar, and this will be the outline of my talk. So the reason I wanted to show this, my previous results and then my current project, is that recently, as you just mentioned, I started to work at Princeton. Actually, to be more precise, as a part of the fellowship, I have to be at Princeton. So it's not a visiting, but I'm really formally there. And I will introduce myself quickly, and then I will explain the concept of information-theoretic secrecy and my Marie Curie project. I will explain my previous work and then current work through two basic examples via cooperation to improve the throughput first, and then I will try to explain how cooperation can improve the security, more precisely the information-theoretic security in the system. And basically, I consider two possibilities with jamming and with relaying. So jamming meaning you jam the evil guy, the eavesdropper. And I will leave some time for discussion and ideas. So this is my previous resume. I got my bachelor at the university in Skopje in Macedonia in '98. Then I did my PhD studies in Switzerland with some part of my PhD at nuclear research in Helsinki. I worked for a startup company in Switzerland before I joined the University of Hawaii at Manoa as a research scholar. After that, I did my postdoc at the University of Oslo. And recently, I got this Marie Curie Fellowship, which is a 3-year project, 2 years at Princeton and 1 year at Cape Town. So, can we? Yeah. Okay. The origins of the information-theoretic secrecy are described in the first paper by Shannon in 1949, and this notion of secrecy is widely accepted by the community. Even the cryptographers that work in computer science, they also accept this definition of secrecy. So the story is the following: we have two parties. Alice wants to communicate to both, and there is some message that has to be transmitted. So there is a third party called Eve that eavesdrops the message. And in the original example by Shannon, there is no noise in the channel. So Eve basically gets the perfect transmitted signal from Alice, the same as Bob. And in order to hide the message, then there must be some key, such that Eve cannot get the decoded message. The goal for a perfect secrecy is to ensure that this conditional probability is equal to the original probability of the message. Or in information theory words, it means that this conditional entropy, that is called equivocation, has to be equal to the original entropy of the message. Or in a simpler way, the mutual information between Alice and eavesdropper has to be 0. So that's the Shannon, the original Shannon definition. So it's basically saying that there must be no flow of information between the sender and the eavesdropper. This is a bit a pessimistic model because we assume there is no noise between Alice and Eve. I mean, in practice, there are more complex channels like noisy channels. So let's go like 3 decades later. Weiner introduced the Wiretap Channel, and in this channel there are there is some noisy channel between Alice and Bob, and then there is a noisy channel between Eve and the lines. And at that time, people were more interested in wired communication, so that's why it's called a Wiretap Channel. A more general model would be to have a whole channel here, so that's more appropriate for wireless purposes. And there are two aspects here. So one is the reliability aspect, so that means the communication between Alice and Bob must be reliable, meaning that the probability of error of erroneous reception at the receiver must be fairly small, and the other is the security aspect, and the security aspect is, as I mentioned earlier, that the mutual information basically between Eve and Alice must be 0. So we like that these two are satisfied at the same time, and that's actually the secrecy capacity. So that's the largest rate at which both of these reliability and the security aspects are satisfied. We have positive secrecy capacity only in the degraded case, meaning that only in the case in which the channel between Alice and Eve is weaker than the channel between Alice and Bob. So now in the following talk I will explain basically how to make the channel to be degraded, or in other words, having positive secrecy capacity. So for the time being, to remember is that this information-theoretic secrecy is the ability of the physical layer to provide security beside the reliability in the system. And basically, I will discuss the secrecy capacity in this shape, that the secrecy capacity is basically the difference between the capacity between Alice and Bob, between the sender and the receiver, and then minus the capacity between Alice and the eavesdropper. And if this difference is positive, that's the secrecy capacity, otherwise it is 0. Let's consider a simple model. So we have again the same actors in the system, and imagine we have a perfect channel between Alice and Bob. We have binary transmission, binary channel, and we have very nice channel between Alice and Eve. So basically here, if we transmit some message from Alice to Bob, we get the same message, but the message at Eve is just disturbed by noise, binary noise 1/2, and in that case, the mutual information between Alice and Bob is 1, and the mutual information between Alice and Eve is 0. So this is a very trivial example, but just to show that if the eavesdropper is degraded, then we have perfect secrecy without any, okay, supposed to be written no key, so without any key in the system. Let's say we have a Gaussian example. So we have a message that has to be transmitted over a fading channel with the full fading coefficient and additive Gaussian noise at Bob. So there is another pair of fading coefficient Gaussian noise to the eavesdropper. If we define the instantaneous SNRs to Bob and to the eavesdropper as gamma n and gamma w, then the secrecy capacity is either the difference between the point-to-point capacities or 0 if the signal-to-noise ratio is small or equal to the signal-to-noise ratio of Bob is equal to the signal-to-noise ratio at Eve. So if we go over the layers, where is in which layer is our story is of course on the physical layer, because we have different types of security on different layers. Some of them are famous through their acronyms like SSL or VPN or WPA, and we are basically interested in this physical layer security. More specifically, we call it Information-Theoretic Security because the method is information-theoretic based. There are other types of security on the physical layer also. what are the challenges? The first challenge, the most difficult thing is that the perfect secrecy cannot be always guaranteed because of the broadcast nature of the channel. And if we allow that the eavesdropper can arbitrarily coach the sender, then the eavesdropper will have a very strong channel, and it can go stronger than the original channel, and then we don't have the degraded case of no perfect secrecy. So we will see how to make a system that is less vulnerable to such situations. Another challenge is that the system has to be decentralized, so we're interested in decentralized systems. So we really want to have a network in which users can communicate and cooperate freely. And in such a system, we really don't know if the cooperating nodes are good or bad. So we really have to study a situation in which we have Byzantine nodes, for which we are not sure whether they are our friends or foes. And our goal is really to keep all the malicious nodes, if we know them, or even if we don't know them, we want a more robust system, to keep them ignorant of this transmitted data. So in information theory words, we really want to keep this maximum equivocation, or we really want the mutual information to be zero towards these malicious threats.
Like the example that you gave a while back, if you have instantaneous SNR such that the SNR for the Alice Bob channel is better than SNR for the Alice Eve channel, then the instantaneous secrecy capacity is positive.
Yes.
But if you consider a long duration of time where the SNRs are time varying and the average SNR for Eve is better, but at any given point of time it may be worse, does this correspond to zero secrecy capacity?
No. So it's I was describing only the instantaneous secrecy capacity, but you can.
How do you define secrecy capacity for the thing? I mean, obviously we're defining capacity in the asymptotic regime where you're allowed to use the channel infinite number of times and approaching your block as approaching infinity.
Then you have to define ergodic secrecy capacity. So just expected value of the instantaneous secrecy capacity. But it's a good question. So our central question is in this project is how to design a cooperative decentralized perfectly secure system. And what is the motivation? The motivation is that the future internet will be wireless and there will be many objects. So sometimes they use this terminology Internet of Things. And in such a situation, it might not be always easy or practical to apply the current conventional secrecy methods like exchange of keys among so many objects. Like we're talking about thousands of objects in a small area, and it may also not be easy to apply this secrecy on all this or all the layers. So it could be nice to have a robust method that will be applied on the physical layer, and then will just ensure that we have a secure transmission. And also these methods of physical layer security are a good possibility to combine it with the classical methods. So maybe at the end of the day, we can use them just for exchanging the keys. Then the main communication will be done having these keys exchanged by the physical layer. And then, since we don't have too many possibilities, we're thinking that maybe by cooperation we can improve the secrecy. And I will, in the following part of the talk, I will explain a couple of methods. And the basic channel models that I started to consider are the model in which we have one sender and many receiver, and we can have some malicious nodes, and also the multiple access model in which we have many receivers, many senders, one receiver, and the most interesting one is the interference model in which we have many senders, many receiver, and many receivers, and then we can have a malicious node. The cooperative scenario includes all types of relay channels with some eavesdroppers around. So we will see shortly this model and this model. And so the relays can be in parallel or in a multi-hop way. And we can have some general models also, as well as the so-called broadcast relay channel and multi-access relay channel. A realistic scenario would be to analyze a system in which we have more senders, more receivers that can cooperate, and then in the system there might be more than one eavesdropper. And what if we allow that the eavesdroppers can also cooperate? So that will be a more challenging situation. First, I will explain a simple scenario in which we see how cooperation can improve the rate in the system. And in system where we have cooperation, a natural tool to use is the game theory. And here I will explain how we use the game theory to study such a simple cooperative network. So imagine we have 4 nodes, and node 1 wants to communicate to node 3, and node 2 wants to communicate to node 4. And node 3 and 4, they can only receive the signal, but node 1 and 2, they can receive and transmit. So basically 1 and 2, they can cooperate and help each other to improve the rate efficiency in the system. So say that during the periods that node 2 is silent, it can help node 1 to relay its transmitted data to node 3, and vice versa. While node 1 is silent and node 2 is transmitting, then node 1 is a relay, it's a helper to node 2. And just for simplicity, we assume time sharing model in which during some portion of time we have this communication between 1 and 3, and 2 is a relay here, while during the rest of this slot is node 2 is transmitting to node 4, and node 1 is a relay. So we model it on a standard way, such that at node 3 we receive what is transmitted from node 1, attenuated by the corresponding channel coefficient, what is coming from node 2, and then additive noise. While at node 2 we have only what is transmitted from node 1 plus the noise at node 2, and similarly for nodes 4 and 1. These channel coefficients, we assume that they are related to the distances between the nodes, and we use the pathos coefficient beta. So basically the model is fixed, so no one is moving. And we define the game in such a way that we denote by k the fraction of power that, let's say k1 is a fraction of power that user 1, node 1, uses for its own purposes, and the rest of it is used to help node 2. So this is basically the power that is used for all purposes, and then the rest of it is to help node 2. That's for user 1.
So each node is transmitting and receiving in the same time slot.
No, actually, that's a slight simplification there, so that we could get mathematically closed form results. So we consider time sharing. So basically, during the first period of time, node 1 is transmitting to node 3 by this much power, and node 2 can. How do you say? Yeah, actually, that's true. So I assume full duplex. Node 2 can listen and transmit at the same time. You can consider also such a system in which you can have a half duplex that can listen and transmit. But here I assume that the duplex. So during this first portion of the time, node 2 is using 1 minus k2 times b2 portion of the power to help user 1. And the game is each user should maximize its own rate. So basically, if we want to see what is the Nash equilibrium in the game, so Nash equilibrium is a situation in which while playing the game, user come to a position in which they do not change that position, so they are comfortable with that. Any changing of that position will lead to lower performance. And the strategy of each user is here to choose how much it will help the other guy. So basically, choosing K1 and for user 1 and choosing K2 for user 2. And if they do not cooperate, if we leave them like this, they will be selfish. I mean, user 1 will choose K1 equal to 1. User 2 will choose K2 equal to 1 also. And we'll basically have two point-to-point channels. And that's the Nash equilibrium in such a system. And no one has an incentive to divert from this to this point. And that's not optimal. So if we allow them to cooperate, if somehow, if this is not the goal in the game, they have to choose some K1 and K2 that will be better for the sum rate of the system. And how to measure this efficiency of the Nash equilibrium? It's we compare the sum rate and the Nash equilibrium to the most optimal sum rate, to the optimal sum rate with respect to K1 and K2. And this is, of course, centralized because they are not aware. So there must be someone to see what are the optimal K1 and K2 depending on the position. And in game theory language, the worst equilibrium efficiency is called price of anarchy. So that means the performance of the worst Nash equilibrium. And in this work, we were studying the bounds on this price of anarchy, and then we see that there is a big room for improvement. So we found the lower bound, like closed form solution of the lower bound of the price of anarchy. It's surprisingly enough, it's the lower bound is related to only to the powers and the beta for any position of the nodes in the system, which is kind of interesting result. And moreover, if the powers are equal, then it depends on beta. And the upper bound is also it's a function on the powers and the beta, and so this is the upper bound, and where rho is a solution to this transcendental equation. But we can still upper bound with having a looser upper bound, and we get something that is easy to remember. So what does that mean? That means just by simple words saying that if we allow users to be selfish, not to cooperate. That means they can achieve at most this much of what is possible by cooperation. And imagine that beta is equal to 3 in some mobile environments, so that's only 12.5% of efficiency. So there is a big room for improvement by setting up some mechanism for cooperation to motivate the nodes to cooperate rather than being selfish. And if we try to plot these results, the lower and upper bounds, we see that we are as a function of beta. And first we take that the powers are equal. We see that we are somewhere between this upper bound and lower bound, and it's really like big room for improvement until the most optimal performance. What is interesting here is that if the powers are equal, then this tight upper bound is the tighter upper bound is close to this weaker upper bound, but it's far away from the lower bound. But if we go further, if the two powers are not equal, then the tighter upper bound is really like much tighter than this easy to remember upper bound, and it approaches the lower bound. So we also see even in the general case that the bounds are getting very tight for larger beta. If you further just change the difference between the powers, then it's really like the upper and lower bound approach. So this was just an example of how to use a game theory to studying the equilibrium behavior of the users with respect to the rates. So now I'm going to jump to examples with respect to the secrecy capacity. Just remember for now that nodes should be encouraged to cooperate, so they should not be allowed to be selfish in general. First example is the cooperation with friendly channels to increase the secrecy capacity. So we have a situation in which we are in a bar, we have a table, and then there is Alice and Bob. So Alice wants to transmit some secret message to Bob, and Eve is listening. So how to make a perfect secrecy between Alice and Bob while Eve is listening? We have some friend that starts talking to Eve and starts disturbing her by decreasing her signal-to-noise ratio. And we might have more friends. So all of them start talking to Eve, and Eve is getting worse and worse channel. And in the meantime, they also produce some noise for Bob. So we have to take into account that the signal-to-noise ratio of Bob is also disturbed. But we hope that the cooperating relays, they more disturb the destination, actually the eavesdropper, and while originally the eavesdropper maybe had better signal-to-noise ratio than Bob, at the end, after this disturbance from the friends, she gets worse, and then the secrecy capacity becomes positive. So we also have to be careful here. If some of the friends is a Byzantine friend, maybe she would listen to our information and then cooperate with the eavesdropper. A traitor. A traitor, yeah. And now in this example, the game is basically this the interaction between the original source and and the jammers or her friends. So basically, she buys jamming services from the friends, and they set up the prices for their jamming power. So if this guy drinks I don't know, soft drink, and this guy drinks whiskey, then maybe she will buy services only from this guy. And it will be enough to make the secrecy capacity better. So it's really a trade-off, and by jammers then decide how much power they will invest by they will sell actually to Alice, and then they will use this power to shout at him. So in this system, really, as model, the geometry matters, because I'm using still the distance and the pathos ratio for simplicity, otherwise it's too complex. And then there is always a trade-off between for this price of the jamming service, because if the jamming service is too expensive, then the jammers, they sell less power, or they don't even sell power. Otherwise, if it's too low, they may not be happy with the dollars they earn from the service. This is the type of the game. It's called Stackelberg Game that we use here. So it's a two-step game in which we have leaders and followers. So the leader is Alice in this case. So she decides how much power buys from the jammers, and then the jammers, they follow them by just modifying their prices. So they decide on their strategies to set up the prices and then modify it, and then the leader buys the power. The leader, yes.
In this scenario, does it make a difference if the eavesdropper can eavesdrop the trading? In other words, is it necessary to keep the interaction between the buyer and the seller secret, or not?
Yeah, that's actually a good point. So I assume that this overhead is perfectly secret. So if we want to be more precise, we have to assume also that the eavesdropper is able to listen to that. But then I think it's getting pretty messy.
I see it could go both ways. When the active communication starts, the jammers transmit noise. The fact that the eavesdropper knows that they're going to transmit noise doesn't help the eavesdropper increase her channel capacity.
Yeah. No, I see that point, but
it could go both ways. That's what I'm trying to visualize, and I can't tell in my mind whether secrecy makes a difference, whether it's certainly not necessary, because a jammer that jams your signal for the eavesdropper is effective even if the eavesdropper knows that there is going to be a jam.
Yeah, no, that's true. But this is really like really the story is simplified in the sense that I really consider that everything that comes from the jammers to the eavesdropper, it's a noise that really it decreases the signal to noise ratio.
Yeah.
So all it is. So I didn't consider the situation in which the eavesdropper is aware that this is a noise, and it just is ready to keep it away. But maybe it's.
The eavesdropper cannot keep away noise based only on the knowledge that there is noise.
That's true. Yeah.
In other words, if I know that I'm getting signal from you, and I know a priori that your signal power is X, and there's going to be noise power of Y, I still get a signal to noise ratio of X over Y.
Yeah.
And if your transmission rate is higher than that, I'm out of the game. Even if I know a priori the levels. So but I can't tell whether there's any advantage whatsoever to the eavesdropper in knowing what the jammers are going to do.
Yeah, sure, but I cannot immediately say how remodel the whole system here so that I take into account this awareness of the eavesdropper.
So for now, you assume that the eavesdropper will be unpleasantly surprised when transmission starts.
Yes.
And has no idea that there are cooperating jammers.
Yes. So that's the story. It's a very simple story. But to be more robust, I totally agree that we have to allow that the eavesdropper is aware of any other communications system. So basically, that's actually the power of the Shannon proposition, that Shannon assumes that the eavesdropper is first aware of the code book that is used by the original pair, communication pair, and secondly, the eavesdropper is computationally very powerful, so it can break any keys in the system. And Shannon says, even if you have such an eavesdropper, by using the secrecy capacity, if you're able to find a good code that has a rate below the secrecy capacity, even if the eavesdropper is aware both of the code books and it's really powerful, like it has the most powerful equipment in the world, still will not be able to receive that. So there's
in the static situation when there's no game. I have not thought about when there's a game, but in the static situation when there's somebody who helps you, helping here, George has studied this in detail, and the fact that the jammer knows that there's a helper doesn't really help him.
I mean, that the eavesdropper knows that.
Yeah, the eavesdropper knows that there's a jammer, and that really doesn't help him at all.
That would be my guess, even with the game. I mean,
Yeah,
if the eavesdropper,
offhand I would say that, but I haven't thought through.
my guess would be that the game can be done in the open,
Right.
public domain. Everybody knows the outcome of the game, and the eavesdropper is still stuck as long as you stay below the secrecy capacity.
It's a word thinking about this. It will be the third thing in the Shannon. Shannon was not thinking about the game.
That's most likely right.
Yeah, if the eavesdropper is aware of the game, yeah, then it's a better model to assume that he knows, and then he or she knows, and then act correspondingly. So basically, we were studying the aspects related to the Stackelberg game, like the equilibrium and the achievability of the equilibrium by a distributed algorithm, the convergence and the comparison to central scheme. I will not go into details on this because we don't have too much time, and I'll just comment some of the results that we saw that this kind of jamming improved the secrecy capacity, and then this interaction between the source and the jammers, and then allows to achieve some equilibrium, and then there is a distributed solution. As I mentioned already, there is a trade-off for the jammer's price, and we also have a following work on distributed option theory, in which jammers, they put they set up their prices, and then there is actually they auction their the prices of their power, and then the sender decides which one will be chosen on this auction.
Does Alice know the channel between each jammer and Eve, and the channel between each jammer and Bob?
No, Alice doesn't know. So that's the assumption. The next step is to consider the situation in which this.
Bear with me, I have another question before you move on. Have you looked at the possibility of Eve also doing some jamming? Eve can put out a jamming signal that would be known to Eve. So it would be seen as noise by Bob. But Eve would be able to cancel it out.
Force off and put out a stronger signal.
Huh?
And force off and put out a stronger
Well,
signal.
first Alice put out.
Alice,
Yeah, that's right. That's what I'm thinking.
I remember at the very beginning, I started to think about, actually Frederick motivated me a lot to put this proposal, and we started this discussion 3 years ago at Newark Airport. That was our first discussion in the area, and then I put up the proposal, and that was a good proposal, and I got the fellowship. So at that time we were discussing that there are two possibilities to consider two possible situations with respect to the jump to the eavesdropper. So one is a passive eavesdropper that listens only, and our goal is really to make it equal, to make the initial information 0. And the other one is active eavesdropper that in addition to listening it can send some jamming to the receiver. And there is even terminology like usually they call the passive eavesdropper Eve and the active one Jasper. So I remember the discussion that we had at the very beginning, but so far I was really like ignorant towards the second example, which I think that it's a good idea to consider that the eavesdropper is also not
Or for that matter, the eavesdropper has a Byzantine friend that cooperates by sending a signal that is known to the eavesdropper but unknown to the.
Yeah, that's on my wish list now to consider, especially this Byzantine, because it's really like you don't know what to expect from the nodes around you. So it's if you're able to find a method that it can be robust, like also taking into account the Byzantine behavior, and it will be a good.
I remember the story of the king who was hard of hearing, and in order to hear better what people were telling him, he had a drum in the background, because he was deaf to the tones, to the pitch of the drums, but most people were not, so they would talk louder.
okay, that's.
Actually, the case that you're saying, with an active Eve, she will always be able to force them to have 0 secrecy capacity. She yells loud enough. Bob hears nothing, but she can always subtract it.
Yeah.
No, it seems like a very strong point.
No, yeah. It's not as simple as that. You're right somehow, but it's not as simple as that. I mean, if she does not have friends, you have friends, you can still manage with your friends to worsen her signal-to-noise ratio enough, so the secrecy capacity is still positive, but what if she has friends on top of that, or some of the nodes are Byzantine and you're not aware of it, so it's, in that case, she's very powerful.
But in answer to that, you have to assume that there is a certain dynamic range that Eve can achieve. Obviously, if you're transmitting 1 kilowatt and trying to receive a nanowatt, you can't do that.
Okay, so moving ahead. So now, in addition to the jamming, I assume that the relays they can also take part of helping the source by relaying the signal itself. So I have the same scenario. So here I call the eavesdropper malicious node, and I have a relay that helps the source transmitting the signal to the destination. So only by the relink, it strengthens the capacity of this link, and therefore improves the secrecy capacity. So we want to point also here that now it also affects the capacity between source and the malicious node, because the malicious node can listen also to this signal and combine with them appropriately. And let's say we have more relays, and all of them they leak some information to the malicious node. But we want it to be like more general, and assume that the source and the relays are not that stupid, so they can, in addition to the useful signals, they can dedicate part of their power to jam the malicious node. So in this scenario, I also allow the source to jam the malicious node with part of the power, as well as any of the relays. And just as a reminder, the equation about the secrecy capacity. So basically, in this in the previous scenario, we were increasing the secrecy capacity by decreasing this part of the equation. So only the capacity between the source and the malicious node. But here we do both. We decrease this and then we increase this part. And let's see how the secrecy capacity can be studied. I chose a geometric way of studying it, and you will see shortly.
The jamming that occurs from R's and S's to M doesn't affect me.
No, here I assume that relays are smart enough that part of the power that is used for jamming jams only the malicious, and then really the one that the rest of the power is used to transmit to relay the information to the destination. It's actually I assume a more general model, but then to get the results in a pictorial form, I really have to do some many assumptions here that will simplify the model. But I just wanted to show some results that are of interest.
Bear with me. I'm sorry, one more question. In this model, how does the node D combine signals from the various relays as well as from the original transmitter?
So it's just I assume that it's just combining the all the transmitted signal like in a MIMO way. So
it's maximal ratio combining,
yeah.
essentially.
So it's like I basically have a relay channel between the source and the destination, and I have multiple relays here.
Okay, so you assume that each relay has enough capacity to fully decode the message.
Yes.
So that each relay sends an exact duplicate
Yes.
of the message.
Yes.
Okay. And then you assume that that node D takes all the received duplicates
Yes.
and combines them optimally.
Yes. Yes. And I assume like full duplex relay. So it's basically here I wanted to. I didn't go that much into details to explain this relay scheme, because I used again bounds on the relay capacity, because we don't have a closed form solution in the relay capacity. But I just wanted to point out that we can use this type of cooperation to increase the secrecy capacity in this case, not only the regular capacity. So again, standard model for at the destination, we have what's coming from the source, what's coming from each relay. So we assume M relays, and then additive noise. And at each relay, we have what's coming from the source, attenuated by this channel coefficient. We have power constraints at each source and each relay. And again, Atlas coefficient model with this beta. The noise is Gaussian. The eavesdropper. Here we assume some specific model that captures the location of the eavesdropper. So I say that if the eavesdropper is too far from the source and close to some of the relays, the eavesdropper will be able to listen more to the relay than to the source. So somehow I exclude the possibility that the eavesdropper is able to listen to anyone in the system. So I introduced two more coefficients here. One is I denoted by Q, and I call it like synchronization coefficient. So how well the relay is synchronized to the source, And then for each relay, I introduce some other coefficients k. So this one should be from 1 to m. And so k represents how well the eavesdropper is synchronized to the relay. So these q and k coefficients, they are between 0 and 1, meaning that having the most powerful eavesdropper, that means q is equal to 1 and k equal 1, so that means that the eavesdropper is somehow perfectly synchronized with everyone in the system. And then I assume to be more general, I can assume that was part of the question you asked, that some part of the power can be used for jamming the malicious node here and here, but just for simplicity, to reduce the number of parameters, because I already have n plus 1 parameters here, and then if I have another n plus 1 parameters here, it will be too complex. So just by simplicity, I assume that the rest of this power is used for jamming, and the rest of this power is used for jamming. And then even n plus 1 parameters is too much to get some like particular results. So I go further on. I assume that two models, like model 1 is that this synchronization parameter is related to the distance between the malicious node and the source, and then the corresponding synchronization parameter of relay I is also related to the distance by negative exponential. I also assume another model to the negative exponential square. So I don't have any practical like proof to introduce such models, but I just assume it because these functions are between 0 and 1, and it makes sense somehow, since if the eavesdropper is closer to the source, then this is larger, which makes sense, and then if it goes further and it approaches some relay, then this will be larger and this smaller. So don't ask me if you think this is not logical. Maybe it's not logical, I don't know, because I don't have practical feedback for such type of correlation, but mathematically it's possible, and then we get some results just to present my idea on this. I use the bounds for the relay capacity from the paper of Gaspar and Fetterly. So I use for the upper bound the cut set bound, and then for the lower bound is some compressor forward rate. And I will not go into details explaining all these coefficients, but just to see that these are some log expressions related to the powers of the relay and of the source and all the relays. And for the malicious node, as I explained, I consider that the useful signal of the relay is scaled by this synchronization coefficients to the source and all the relays, and then the rest of it somehow scaled by y minus q and 1 minus ki. To be more precise, to be more robust, it would be better to have here q prime and 1 minus ki prime, but just to lower the number of parameters, I assume here 1 minus q and 1 minus ki. And then we start talking about secrecy capacity bounds, because here we don't have the exact expression, because we are missing the expression for the relay capacity. So we have upper and lower bounds. And now I introduced for the first time here three definitions, like the geometrical area in which the secrecy capacity is positive. We call it secrecy region. So that means in this region we can have some eavesdropper, but the eavesdropper will not be able to listen anything. The complement of this region, I call it vulnerability region. So that means in the vulnerability region we are not sure that the secrecy actually the secrecy capacity is 0. So we are not sure that the eavesdropper is not listening to us. And then the third one is the normalized vulnerability region. So I want to compare this region to the vulnerability region of a circle centered at the source and then has radius as much as the distance to the destination. So this is the generic case in which if we have a channel based only on the distances, that means this is source and this is the destination, and that means that if the eavesdropper is inside this circle, then the channel to the eavesdropper is stronger than the channel to the destination. So basically, the eavesdropper must be out of it. So using this terminology, the vulnerability region is this circle. The normalized vulnerability region is 1. So I want to be just to compare how the vulnerability region in my scenario compares to this normalized vulnerability region 1. Without cooperation, we can get a closed form expression of the vulnerability region. So basically, we have to solve this equation where the capacity is smaller than the capacity to the malicious node, to the eavesdropper. And if we solve this equation, we can get some type of closed form expression that depends on this synchronization coefficient and the signal to noise ratio, which is defined by this equation. And naturally, as I said, if Q equal 1, then the vulnerability region is really a circle defined by this radius, which is equal to exactly to the destination. So if Q is smaller than 1, then the radius of the circle is shrinking, and it can be even 0 for some combination of Q and gamma. Let's include this one relay, and assuming that the power of the source, the relays, and the noise is 1, and beta equal 2, and we assume model 1, so this exponential model. In this case, we get the vulnerability region as follows. This is the source in the center, this is the destination, and this is the relay. And the red dots are the positions of the eavesdropper in which the secrecy capacity is positive. So that means it leaves the white region as the vulnerability region. So in the white region, the secrecy capacity, if the eavesdropper is placed in the white region, then the secrecy capacity is 0. And if we compare it to this to the initial vulnerability region, we see a good improvement. So this is the lower bound, and that is the upper bound on the vulnerability region.
I'm puzzled by the fact that the destination is in the red region. If the eavesdropper is in the same exact position as Bob, doesn't the eavesdropper get the signal just as well as Bob?
Yeah, actually the question is very logical, but in this case it is not like this, because I assume this synchronization coefficient. So because of this particular assumption, I would say, since I assume that basically the channel to the destination is this relay channel, but the channel to this dropper would not be a relay channel, but it will be like a kind of multiple access channel from what is coming from the source and the relay, attenuated by this interference. So it's basically the assumption that I don't have a relay channel to the eavesdropper. Yeah, but I agree it's a confusing if you don't think about this. It's really like you think how is it possible that it is placed here, but it's on the other hand it's not very unnatural to assume like this, because I really assume that I have friends to help me, but he doesn't. So that's the point. And then if you further increase the number of relays, then we really see improvement in the secrecy capacity in terms of this vulnerability region. So the vulnerability region is shrinking, and it's starting to approach the source and all the relays. And if so, these are the lower and the upper one. And if I further increase the number of cooperating relays, then really get better and better situation. So then, just to be clear, these red dots, these are the position of the eavesdropper in which the secrecy capacity is positive. But we may also not be satisfied with how big is the secrecy capacity. So this is really study on how we improve the region in which we have perfect secrecy. So we may, because let's say the eavesdropper is here, and then we have positive secrecy capacity, but it is, I don't know, one bit per second. We may not be satisfied with this. But this is not, it's not the focus of the study, so for time being, I study only on this. And if we try to see how these bounds depend on the number of the relays, so we see that it's really improved by using more and more relays. And we can notice that this improvement is less and less by increasing the number of relays. So it's really enough to cooperate with a couple of relays, like 3, 4, and it's enough. Then it flattens out. This is also the performance of the bounds for model 2. So for model 2 we have a bit worse situation than model 1. So model 2, by model 2 I mean this negative exponential square of the distance. And if we study what happens if we place all the relays on the line between the source and the destination, we have better results, which is logical. It's the most efficient relay if you choose it on this line, and we show the results for model 1 and model 2, lower and the upper one. So again, to summarize, again we see that the cooperation improved the secrecy capacity, and this improvement is not really measured by the secrecy capacity, by the improvements of this vulnerability region. And as I mentioned, that the improvement is less as the number of relays increases, and yeah, the most dramatic is by using only one relay. So we noticed that it's better to place the relays on the line, of course, and this is actually related to your comment that somehow the model is such that the source has more benefit from the relays than the eavesdroppers. That is our assumption. So I wanted to open the floor for some discussion. Before that, I just wanted to show how this how my project is organized. So my project is related to this IT security, like what are the models, some using feedback and relaying, and the game theory like methods, cooperation, the equilibrium analysis, mechanisms to improve the situation and options, and of course coding theory. What are the secrecy capacity approaching codes? It's not an easy task at all, and it's a big part of the project. How I want to relate my project to other related topics is that how to connect this information-theoretic security to cryptography-based methods, so like maybe using it for key distribution. And then I'm interested, what are the scaling properties if we start to increase the number of sources, destinations, cooperating nodes, and how it will work in a distributed scenario. Another interesting link is to the social networks, like how these aspects of social networks, trust, privacy, security can be with this, I would like to thank you for coming to my talk. And